Welcome. In this video I will state and prove a formula for the derivative of a power function with non-zero integer exponents. Alright, so let's put that on the board. So we have that the derivative of x to the power n is equal to n times x to the power of n minus 1. So what happens to these integer powered power functions is that the exponent falls down and then gets reduced by 1. This is really nice. It's really beautiful and very intuitive and visual almost. It kind of looks like a production line in a factory, right? It kind of boom falls down and then the next one line comes along. Beautiful. Well, let's look at the proof, shall we? The way I'm going to prove this is I'm going to do a proof by induction. All right? I'm going to show that we have some basis case, and as soon as we have that basis case, I will show that every time we have one case, we can show that the next case is also true. And that creates this domino effect that the base case proves the next case, proves the third case, and so forth. All right? So when we're doing these induction proofs, we always need a base case, okay? So the question is this true when n is equal to 1? Well, if n is equal to 1, we just have x, right? X to the power of 1, right? Well, we know what that derivative is. It has a constant slope of 1, right? So this is good. Right? Beautiful. I should add that I'm assuming that there's no constant factor here, because if I have a constant factor, I can just scale the derivative afterwards. That's not the important part of the derivative. That's not the complex part of the derivative, right? So if I have a constant factor, I can just multiply it afterwards when I'm done finding the derivative. Beautiful. All right, back to this. So I have this basis case n equals 1. All right. Well, now let's assume that n equals k is good. That's an assumption. I assume that I have one case. Then I want to show that the next case is also true. Again, this domino thing. If I have one case, then the next case is also true. Okay? So let's check the n equals k plus 1 case. Right? So when we're finding the derivative, we always find the secant slope. All right? So we start by finding the rise of the secant slope, which looks like this. Right? In our case, we have the function f of x is equal to x to the power of k plus 1. Beautiful. All right. Now I'm going to take this thing here and I'm going to expand into product of two factors. One with k of these parentheses and then one extra parentheses. I'm going to do something similar with this one. I'm going to expand into x to the power of k and then multiply it by x. All right. So what we get is we get x plus h to the power of k times x plus h, and then minus x to the power of k times x. Absolutely wonderful. All right. Now we expand this parenthesis. So we get x plus h to the k times x plus x plus h times h minus x to the k times x. All right. So this factor here and this factor here, they have the same factor of x. Right? So we can put that outside of parentheses. So we get x, and then we have this thing here, x plus h to the k minus x to the k. And then we have plus x plus h. Look at that. We have the rise of the previous case. We have the rise of the previous n. which is exactly where we want it to go. Okay, so what this is, in reality, this is the rise of the secant slope. So the difference in the y values. So we still need to find we need to divide by the run, the difference in x values if we want to find the slope. So we still need to divide by h here. All right. What happens here is these h's just cancel, and what we get here is this again as the secant slope for the previous case. But we assumed that was true. We assumed this formula was true for the previous case. So what happens here is that this goes, as h goes to 0, this goes simply to x times k times k, x to the k minus 1 plus, oh, shoot. No, it's good, it's good, it's good. I think xk bum 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 plus x. Feels like I'm missing something. Yeah, shoot. This should be to the power of k because it's from this thing here. This should still be to the power of k. I look weird. All right. So as h goes to 0, I can just replace this by a 0 because it doesn't cause any issues. So this is going to be x to the k, right? Which is equal to, well, we have x to the k minus 1 times x, which is just x to the k. And then we have a k of them, and we have one of them. So this becomes x plus 1, x to the k, which is exactly what we wanted to show. Ooh, yeah. That's it. That's beautiful. All right. So what we've shown now is this is true for all positive non-zero integers. Wouldn't it be nice if we could do something similar for the negative integers? Well, you can. You can do something similar for the negative integers, right? So, and then I'm going to do that now. I'm going to do the induction in the opposite direction. I'm going to still have k being increasing, but I'm going to have k increasing having the influence that we're going down. So I'm going to do minus k, right? So I'm going to do this. Again, I need a basis case. I need this, and then I'm going to do this for n equals minus k minus 1. And assume this is true for minus k. And there you go. So I put a minus on all of these. All right? So what happens here? I get minus, 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 minus. I get down to here, I get a minus, and I get a minus 1 here, and a minus 1 here. What I did here is I expanded this parenthesis. But when it's the inverse, I can't do that anymore. So the argument kind of breaks down here. So if you want to check through this argument for the other case, you pause it now and look through it, because I'm going to have to cancel the argument from this section here, because it doesn't work anymore. But we can do something very similar. We can use this classic trick from math. We're going to add and subtract the same term, which doesn't do anything, but makes it look nicer and makes it actually work. All right. So we're going to take here do nothing. We're going to have this and do nothing, and then we're going to add and subtract something. We're going to subtract k to the minus x to the minus k times this weird thing here, and then we add it. So we haven't actually changed anything. We've just made this superfluous term here. And then we still need this last one. Okay. Okay, I gather these two. Because we have a common factor here. So we have x plus h to the minus 1. And then we have, again, this absolute beauty. And that's these two terms. And again, you can see that this is actually turning it into something really beautiful. And then we have The common factors here is just x to the minus k. And then we have this weird constellation here. Okay, well, I'm going to rewrite this as 1 over x plus h minus 1 over x. Okay? Beautiful. All right, so what I can do here is I can expand this by x, and I can expand this by x plus h. And why am I doing that? Well, I'm doing it to get a common denominator. So I expand this by h, I expand this by x plus h. Right? So now I have a common denominator. All right? Which means I can just gather these two fractions, and then we have to subtract the second one right here. So we have x minus x, h. So we can cancel these two. So what's left is simply minus h divided by that thing. All right? Beautiful. Now we can do the secant slope. All right? So a is equal to, well, when we do the secant slope, we need to divide by h through the whole thing. I divide by h here, and I divide by h here. Right? What this absolute gorgeous beauty here does is it cancels with this thing. So now I just have minus 1 divided by this. Right? Again, this, as h goes to 0, goes to, well, this little thing doesn't really do anything. This, by the assumption, by our induction assumption, goes to, this goes to x to the power minus 1. This goes to minus k times x to the power minus k minus 1. Gets reduced by 1. Then we have plus x to the minus k times minus, because there's a minus here, and then x to the power minus 1, and x to the power, x plus h to the power minus 1, but again the h is replaced by 0, so we actually get just x to the power minus 2 here. Absolutely wonderful, because what happens here is, well, we have x to the power minus 1 times x to the power minus k minus 1. That becomes minus k x to the power minus k minus 2 minus, because there's a minus here, x to the minus k minus 2, minus k minus 2, which is exactly what we wanted, minus k minus k minus 1, x to the minus k minus 2. Isn't that wonderful? There may be a simple way to do this. You may be able to put this argument to the same thing, same proof somehow, but because of this weird fraction thing here, I can't really see how you would do it. But if you have a good suggestion, you know where to leave it? Down below in the comments. I would really appreciate that. All right. So the question here is also, once you've done this, how do you find antiderivatives? All right. So now I know how to derive these non-zero integer powers of x. Well, how do I get the antiderivative then? Well, as we know or might know in the near future, the antiderivative is the opposite of the derivative. It's kind of they kind of cancel each other. So that means that the canonical antiderivative, and when I say canonical, I mean that the constant of integration is 0, because that's in effect usually what we use, unless we're doing some kind of numerical analysis. So the canonical antiderivative of x to the n is then going to be 1 over n plus 1 x to the power n plus 1. Well, why is this true? Well, if we take the derivative off the right hand side here, this thing drops down and then it cancels with the denominator there, and we end up with x to the n. All right. Again, there is a constant of integration here. We have a small c here, but again, I'm talking about the canonical one, the one with the constant 0, because that's in fact the one we're going to use in most analyses, unless we're doing specific numerical analysis with some kind of boundary conditions. Yes, wasn't that wonderful? If you have any questions or comments, feel free to leave them in the comment section, and I'll see you next time.